At the end of the last part, we looked at how and why the plates move, and we talked about convection in the mantle, slab pull, ridge push. So here's just kind of a final summary of that, and that moves us on to the different types of plate boundaries. So the first type of plate boundary we want to discuss is the divergent plate boundary. This is where plates pull apart from each other. In the top diagram, you'll see that they have a depiction of continental type crust on top of that plate. And as it pulls apart, we open up what is called a rift valley. So that's what you see in the middle drawing here. On either side of the middle or of the rift valley are faults. In geology, we refer to them as normal faults, not because they're more common than other types of faults, but that's just the type of name that they have. You can imagine that in that rift valley you might get some long narrow lakes, but also because we thin the crust, we reduce the pressure on the underlying mantle, and that triggers melting. Now if you go back and look at this picture, some of that melting might very well be created by rising mantle material, but we now recognize that the primary driver of mantle melting in this situation is the thinning of the crust. So we said earlier that the mantle is a ductile solid. The reason that it's solid is because the pressure created by the mass of all the material on top of it prevents it from melting. It's still quite hot. When you thin the plate on top of it by pulling it apart, that action reduces the pressure and allows molten rock to form. The molten rock then rises up to the surface, and you'll notice we have fractures here in the form of those faults, and that creates a line of volcanoes. These volcanoes, if we were to look at their composition, are very close in composition to the mantle from which they're derived. If we continue to pull the plates apart, we won't be able to fill in the gap by just faulting the existing continental crust. Instead, you'll notice on this bottom diagram, half of the continental crust goes one way, half goes the other way, and we then must fill in the gap with this rising molten rock derived from the mantle. This is why our ocean basins have crust that is relatively thin, remember 2 to 3 miles, because as we form it, we keep pulling it apart, so we never get the opportunity to make it very thick. And it also shows us why the composition of the ocean crust is very close to the composition of the mantle. We're melting the mantle here due to decompression, and so that material is the material that rises up and fills in the gap. So let's take a look at where we would find some of these plate boundaries. One place to look is in East Africa. That's where we find a continent, Africa, pulling apart. We get what's called the East African Rift. It actually splits into 2 branches here. If you look at this closely, for example on Google Earth or Google Maps, you can see long, narrow lakes located in East Africa, and there are also a bunch of volcanoes associated with the East African Rift. If you follow this rift up into what's now the Gulf of Aden and the Red Sea, what you see is that those are examples of a narrow opening. So just as we start to pull the continents open far enough that we're filling that gap in with ocean type crust, we get these long narrow seas like the Red Sea and the Gulf of Aden. They have volcanoes in the very bottom, and some of those actually reach the surface, and that is kind of new ocean crust and new ocean basins opening up. When we pull that apart even farther, we get what we see in the Atlantic Ocean. And you might recall we took a look at the mid-Atlantic ridge in one of the earlier slides. So there it is. There is our rift running right down the middle of the mid-Atlantic ridge. The mid-Atlantic ridge is higher in elevation because it's warm, which makes it less dense. As it pulls away from the mid-ocean ridge, or as it pulls away from that rift where all the activity is, it cools down, and as it cools it becomes more dense and it sinks, and it gets covered with sediment. So this is an example of a mature divergent margin that has resulted in the formation of an ocean basin. And so that's what we have right there. And you can see if you go to the crest of the mid-ocean ridge, you will find a rift valley. It has normal faults on either side. It has volcanic activity in the middle as it continues to produce more material. Now, if we're pulling plates apart somewhere, someplace else they must be pushing into each other, somewhere on another part of the planet. Because the planet is a sphere, unless it's blowing up like a balloon, which it's not, we're going to be losing crust somewhere else. So let's take a look at that. A convergent plate boundary is a place where two plates come together. Now there are a couple of options here to convergent boundary. The first option we're going to talk about involves oceanic type crust. And this could be two pieces of ocean crust pushing into each other, or a piece of ocean crust pushing into a piece of continental type crust. And remember, we're referring to the crust, which is on top of the plate, but the plate also includes that thick, rigid part of uppermost mantle, and therefore the plate is really lithosphere in total. So what do we find there? Well, we find something that's called subduction. And I'm going to toggle back and forth between a couple of slides here so you can see the details. Subduction refers to this plate going down under the other plate. You can see on the left the ocean plate is subducting under continental material, and on the right the ocean plate is subducting under another ocean plate. In either case, as that plate goes down, we get some unique features. First of all, we get a trench. You can see here they have it labeled as the Peru-Chile Trench. They're using the collision between the Pacific Plate and South America here. Here we get the Japan Trench, which is just off the coast of Japan. You can see it labeled on this map down in the lower right-hand corner. The trench marks the spot where one plate goes underneath the other. In order for that plate to go down, it's got to go deep, and that's what gives us the trenches on the ocean floor. So we get a trench. The next thing we want to mention is what happens to that plate as it goes down. Well, you'll notice they've got this orange and red color here indicating molten rock. There it is right there. It's labeled on this diagram on the right, partial melting. So what's happening in this location is this ocean plate, the ocean crust on top, has a lot of water in it. And remember, the mantle down here is solid. It's a rigid solid. And it's solid because it has all this pressure pushing down on it. In this case, the water in the subducting plate upsets that balance. The water lowers the melting point of some of the minerals that are present in this section of the mantle, and that's why we get partial melting. At a divergent margin, we get almost complete melting due to the loss of pressure. In this case, the addition of water triggers partial melting. That means that these volcanoes that are produced when the molten rock gets to the surface are going to have a different composition. They're going to be much richer in silicon and oxygen, and they're also going to have aluminum and potassium and sodium. This is the factory where we make continental type crust. So the partial melting results in a different composition, which gives us continental type crust. These volcanoes are referred to as a volcanic arc. And you'll notice why, if you look at it on a map, here's the Japan Trench. Because the surface of the Earth is curved, when you have subduction, the subduction zone is curved as well, and therefore the volcanic arc associated is curved. If we have two ocean plates interacting, we get a volcanic island arc. If it's on land, the continental crust is overriding and we just get a volcanic arc on land. Sometimes it's called a continental volcanic arc. So we've got our trench, our volcanic arc, our partial melting, all in the subduction zone. What else do we get? Well, there's some pretty intense pressure here. And that intense pressure is going to cause the rocks on the overriding plate to be folded as well as faulted. The types of fault we get here are called reverse and thrust faulting. They're the opposite type of movement of a normal fault that we found at a divergent margin. The other things we see happening here is something called accretion. You'll notice that here in the Peru-Chile Trench, they've got it filled in with something. They show a little pile of material there as well. The subducting plate, usually, especially if it's a little older type ocean crust, is going to have a lot of sediment on top. That loose material does not go down the subduction zone very easily. Instead, it's typically scraped off and ends up on top of or part of the overriding plate. And so that's what we refer to as accretion. So this plate on top is going to get bigger. And it gets bigger, you'll also notice, from this constant volcanic activity. At the divergent margin, we were pulling things apart. So every time we added more molten rock, we opened it up and kept the crust thin. And here, you'll notice our continental crust gets quite thick because we just keep adding more material in the same place, both from the volcanic activity and the molten rock rising up, and some of it just cools before it ever gets to the surface, and the accretion, the things that are scraped off before they can go down the trench. Something else that sometimes happens is that if this subducting plate starts to sink down into the mantle, so if it starts to sink down because of its mass, it will actually tug the front of the subduction zone. And the overriding plate, when it gets tugged, can tear open in the back, and that's where we get this back arc spreading. This was a bit of a mystery to the folks studying tectonics initially. How do you get spreading at a place where their plates are pushing into each other? And that's when they realized the dynamics of this subducting plate going down could tug on the front or on the leading edge of the overriding plate and tear open an area behind the volcanic arc. So these plate boundaries, the convergent plate boundaries with subduction, are very complex. There's a lot going on here. The other thing I have listed on this slide is metamorphism. This is a type of rock we haven't discussed yet. We've discussed sediments. We've discussed molten rock, which is igneous rock. Metamorphic rock forms under conditions of very high pressure and temperature. And you can imagine, looking at this picture, there's going to be very high pressure and temperature conditions here at the subduction zone. So in addition to these rocks getting folded and faulted and accreted, the heat and pressure is going to cause them to alter as well. And so that is our convergent boundary, our subduction zone. And in the next set of slides, we will talk about the other type of convergent plate boundary, as well as a little bit more on accretion, and we will talk about the final type of plate boundary, the transform plate boundary, as well.